Assalamualaikum and very good day everyone. Welcome back to our class on adaptive control and intelligent system. Today I'm going to talk about system identification utilizing least squared estimation. Okay, I have already explained to you earlier in the previous class what is the identification. It is actually a method of measuring system transfer function or some equivalent mathematical description from measurement of the system input and output. So if you have a system and you cannot write the mathematical description of the system, you can then apply some input to the system and collect the response out of the system. And using this set of input and output data, you can use it for using system identification to predict what is the transfer function that actually describing the system, the model of the system. So identification is actually a form of a foundation for analysis that can be used for simulation and control system. So back in 1704, actually identification has been used many years. For example, back in 1904, a person by the name of Halley have used identification technique to predict a comet or an orbit of a comet. Okay, with his limited observation and limited data that he's collected, he able to predict the orbit of this comet, and this comet is named after his name, Halley's comet. All right, and it is actually predicted that the comet will come back to the vicinity of the Earth every 75 years. You have seen it in 1986, and perhaps if you live long enough, you will see it again in 2061. And there are many also papers written about the world pandemic. So there are papers written telling that they're predicting that every 100 years there will be a world pandemic happen in this world. Okay, and in 2020 or rather 2019, we have seen the world pandemic related to COVID-19. So this is a type of identification that use a prediction method to actually predict what's going to happen. Okay, but that is not the limit of identification. There are many applications that can utilize identification techniques. So identification is actually very closely related to modeling a problem. So when you have an observation or a data collected from the system, you can then obtain the mathematical description of the system. There are two solutions for modeling that I can mention in this slide. You can see the first one is analytical modeling. So analytical modeling is like you are splitting up system into several subsystems, and then whose the property are well known, and then you're going to apply some law of physics to this subsystem, and you can build up mathematical model using the mathematical description of this system. Okay, the disadvantage of this kind of modeling technique is it is actually application dependent. It is also sometimes can be time consuming, and also the model that we develop can be very complex. This is an example of analytical modeling of a suspension system. So if you have a physical system like a suspension system, it is a part of a very complicated, very complex automotive system. So one small part of it is a suspension system. So from this suspension system, we can define the input and output of the system that we want to model. Okay, and then from there you draw the free body diagram of the system. Then you derive the mathematical equations describing the system based on all these elements that you have in the system. For example, for the suspension system, it consists of a mass of the body of the car, mass of the wheel, and then its passive suspension system consists of damper and a spring, and the wheel is actually represented by another spring. So utilizing these elements, you write down the mathematical description of it, and then from the mathematical description, you can then transform it into a block diagram. So using this block diagram, we can do prediction, and we can actually predict what is going to happen with supply input to the system. How does the system respond with that supply input? How does the system is responding? Okay, and we can use this as a tools for us to design the controller to control the suspension system. Okay, but for today, I'm not going to talk about suspension system. I'm going to talk about system identification. So it is a model of a system estimated. Okay, mind you, it's not really the actual model, mathematical model of a system like what we've done with suspension system, but rather the estimation of the system using the measurement of input and output of the system. So when you do identification, it's actually using a black box identification. For example, we call it black box identification because we do not know what is the mathematics behind the system. Okay, so for example, the example that I put here is a ship model which actually depend on wave motion. So the ship model, you can write the mathematics describing the ship model. Wave motion, you can write the mathematics describing the wave motion. But when you put together the wave motion and also the ship model, you cannot come out with the integration of these two. So this is a very good time when you want to utilize system identification. Okay, there are some application, the best approach is to combine the two. Okay, rather than having system identification alone or analytical modeling alone, we can combine the two method, and then for these, for example, we have a process. By combining these two methods, we can actually model the process, and then we can then verify the verification of the model, and then using the verified model, okay, we can use that model for our simulation, for analysis, for designing controller, and many more. Okay. All right. So how do we identify a system? So when we have the modeling, the problem that relate to modeling is that there are so many questions that we can talk about. The first one is, how do we cope with the noisy measurement? Number two, if we estimating the transfer function, what are the order that we need to choose? Number three, does the system have a delay, a time delay or not? Okay, is the system a linear model or a non-linear model? And can we use the normal operation data, or do we need to have a specific data set for this kind of system? Okay, so these are kind of problem or questions that can arise when we want to do modeling. Okay, so when we want to model, if the system is as simple as with one input and one output system, maybe we can use a mathematical description of the system. But when we have a multiple input and multiple output from the system, and in fact, let's say the even worse, the system is correlated with noises and a lot of disturbances, then to model this system become very challenging. So during this time, it is very wise if we utilize system identification technique. Okay, the parameter estimation provide a mean of estimating parameter directly from data. So for example, if you look at this slide, when we have input to the system, when we have input to the system, and then this is the input to the system, and then when we actually apply, okay, so we can apply the input to the system, and then we can actually collect the output response out of the system. Okay, using that input and output, we can then use it to model the system. So before we can model the system, we need to define what is the mathematical model that we want to use for the system. Is it linear system or non-linear model? Okay, so you need to define this first. So once you have actually modeled the system, okay, what happens is that you can then find out what is the predicted output using the model that you have done. Okay, using that predicted output, you can then predict using the predicted output, you can then actually compare with the actual output, and then you can get your predicted error. So using the predicted error, we can then later update the model of the system and improve it if possible. Okay, so it depends on which application or which technique that you're going to use. Okay, parameter estimation have been used in many applications. Okay, I have mentioned this before. So for example, for weather forecasting, so in order for you to forecast what is the temperature or what is the weather that is going to happen in a 1 month time, you need to have many data from the previous months. Okay, so you want to actually predict if it's going to be raining or not, if it's going to be snowing or not in certain area. you need to collect a lot of data, the history of input and output data from the previous weathers. Okay, so this is one type of application using parameter estimation. We can also use parameter estimation to model and also to predict what is going to happen in a plant, for example. Okay, so if it's having this kind of input and this kind of output, what is how is the performance in the next 1 hour, for example. So this is a kind of prediction that we can do using parameter estimation. All right, so there's a bridge that you have here. Okay, this is actually a Tacoma bridge. This Tacoma bridge is actually a bridge that is actually collapsed due to vibration. So if we do parameter estimation and we can actually predict the vibration when the turbulence will happen, we can actually prevent this vibration from going towards damaging the bridge, for example. So parameter estimation have a lot of application, and this is some of it. Okay, this is what I want to talk about today. So when you want to do parameter estimation, you need to first and foremost find out what is the model that you want to use for your system. Okay, so are you going to use linear model or non-linear model? So for linear model, is it going to be as simple as y equals to mx plus c, or is it going to be like an ARCS model, first order or second order? All right, so is it going to be ARMA model or ARMAX model? Okay, it depends on how complex or how your system is being your data collected from the system. Is it a very linear model or is it a non-linear model? So you have to have a little bit of knowledge on the system. Okay, then you need to find out what is the model order of the system. Okay, next is what is the data measured? Is it analog data or digital data? Then you need to decide which methodologies that you want to use. Is it going to be a simple least squared or generalized least squared or recursive least squared? Okay, so or are you going to use artificial intelligence, for example, to model this system? All right, so this is there's a lot of things that you need to set first before you can actually do your parameter estimation. Okay, let's say we have no knowledge on the system. Let's say we do not know if the system is linear or non-linear. We do not know if the system is going to be able to be solved using ARCS model or ARMA models, or it is required to have a higher, more complex model like NARMAX. Okay, so if we do not know all this information, what we can do is we can start with the simplest model. So normally when I do system identification, parameter estimation, I always start with the simplest ARCS model. Okay, and then I can try with the lowest model order, for example, model order 1, model order 2, and so on and so forth. Right? So if it can be solved using a lower model order, okay, with a simpler ARCS model, then we do not need to use a more complicated or more complex model to describe the system. Okay, so as for now, I'm going to show you how to use ARCS model. Okay, what does it mean by ARCS model and how to use it using using simple least square. Okay, so this is given a process. Okay, let's say this given a process in this form. Okay, and I want to use an ARCS model. So what does it mean by ARCS model? So when we have okay, so ARCS model is actually when I have input to the system, U applied to a system. Okay, let's say this is the transfer function of the system. All right, and I will collect output from the system Y. Okay, the input and output of the system is known. You give known input to the system, and you collect a known output from the system. Okay, so you want to model the system, then are you going to use this input and this output? Okay, so you're going to use the actual input and output of the system, and then you're going to actually predefine the model of the system. You do not know if the model is correct or not. You're just going to assume, and this is the model of the system. Okay, so we're going to predict the model of the system. Okay, we're going to have it as GS with a hat because it's actually representing a predicted model. Okay, once you have predicted the model, you're going to then find out what is the predicted output from the model, and then you can compare that predicted output with the actual output from your system. From there, you're going to get the error, the predicted error. Okay, so using the predicted error, we can then use this predicted error to update the prediction model if possible, if needed. For example, so if the system is already having a very low error, then you do not need to update the transfer function anymore. But however, if the system is having a very high error, so we can then use that predicted error to update the model so that it can improve the predicted error. Okay, what is ARC's model? Okay, so when I have that input and output, if I can write it in the form of y is equals to b over a multiplied by u. Okay, if it's an ARC's model, then that b is actually a polynomial of bz minus 1, okay, with model order 1. This is ARC's model with model order 1, and that a is equals to 1 plus a z minus 1. Okay, so this is ARC's model with model order 1. All right, so what about z minus 1? What is z minus 1? Z minus 1 is the form of delay of the system. Let me just show you how does it work. Okay, let's say this is the data that we're going to use is digital data. Okay, it's not analog data, but it's a digital data. So I'm going to use discrete data. Yk is equals to, all right, so I'm going to put b, let's call that b1 to represent the parameters of first order or model order 1. Multiply by the input is also of course, if the input is a discrete input, then the output will be discrete output. Okay, so when I have that, all right, so what happens is that if I multiply the yk with the denominator of my model, okay, so I'm going to have yk, if you multiply with 1, you're going to have yk. Okay, and yk, if you multiply with a1z minus 1, yk will be a delayed data. So it's not k anymore, it becomes a delay by 1. So if you multiply with yk with z minus 2, it becomes a 2 delay. So it's going to be yk minus 2. So if you multiply with z minus 3, yk will become yk minus 3. Okay, so that z minus 1 is showing a delayed data. So then I will multiply that b1 with b1 z minus 1. When I multiply that with uk, it will become b1 u k minus 1. Okay, so this is an ARC's model. All right, so an ARC's model. So let's write, let's say I want to predict what's going to happen. I'm going to estimate what happened at time k. I need to know the previous data of one previous data of output and one previous data of the input. So if I have yk, if I rewrite this, is equals to minus a1 yk minus 1 plus b1 u k minus 1. So you can see here, okay, clearly you can see if I want to find out what is the data at time k, all right, so I need to know at least two data. Okay, one is the output response from the previous data, and then the input, the respected input from the previous data. Okay, so we need to know at least two previous input and previous output data. Okay, this is for first order system. If it's second order, then you can then have a guess, isn't it? So if it's a second order, then you're going to have z minus 2 in your equation. Okay, so let me just show you what happens if it's a second order. Similarly, if I have input of yk with ARC's model order 2, I will have b1z minus 1 plus b2z minus 2 over 1 plus a1 z minus 1 plus a2 z minus 2 multiplied by the input uk. Alright, so this is an ARCS model with model order 2. Okay, so if I do cross multiplication of the denominator with yk, what's going to happen is that I'm going to get yk multiplied by 1 is become yk plus a1. When I have yk multiplied with z minus 1, it will become yk minus 1. Okay, similarly, when I multiply yk with a2z minus 2, I will have a2 yk minus 2. Okay, similarly, on the other side, if I multiply b1 z minus 1 with uk, I will get b1 uk minus 1. Plus b2 uk minus 2. So if we have a model order up to n model order, so if you have z minus n, if you multiply z minus n with any u or k, you're going to get uk minus n and yk minus n. So this is how ARCS model with the one model order or n model order looks like. Okay, so let's see, we want to use simple least squared using this ARCS model for our first parameter estimation. Okay, so I'm going to go back and do using a model order 1. Okay, so what happened if I use a model order 1 for my system? Alright, so go back to the previous equation. Yk is equals to minus a1 yk minus 1 plus b1 uk minus 1. Let's say I've given the data as shown in this slide. I have 4 data with time k1, k2, k3 and k4. The data is as shown in the slide, alright, for input and the respective output. Okay, so what I want to do is I want to model the system. This is the data representing the system, so I want to model the system using ARCS model. Alright, so I want to predict what is the value of the parameter of my ARCS model, which is unknown, b1 and a1. So what I want to do is to predict b1 and a1 using least squared estimation. Okay, so if you look at the data, if I start with k equals to 1, alright, so what happened is that I'm going to have y1 is equals to minus a1 y 0, because k minus 1 is 0. Okay, plus b1 u k minus 1 is again 0. Okay, so if you look at here, alright, we do not have the y0 data and u0 data. We don't have data when k is equals to 0. Therefore, I cannot do this estimation starting with this equation. What I want to do is actually I want to use this equation, okay, but I want to actually shift the equation, okay, because it cannot be done as it is. It need to be shifted a little bit. All right, so I'm going to shift the equation by 1. Why do I need to shift by 1? Because it is undesirable to have this yk or u and y when time k is equals to 0, because I don't have the data. Okay, so this is undesirable. Y0 and U0 is undesirable because I don't have the data Y0 and U0. Okay, so I'm going to shift by 1. So what happened is that instead of YK, it's going to be different now, isn't it? Okay. So what happened is that when I shift by 1, YK will become YK plus 1. Okay. Similarly, for YK minus 1, it become YK minus 1 plus 1. So it become YK. Similarly, for uk minus 1, when I add 1 into it, it becomes uk. Alright, so this is how the equation looks like once I have shifted it. Okay, so now then once I have shifted it, then I can start with k equals to 1. Okay, so what happens is that when k equals to 1, I have y2 equals to minus a1 y1, okay, plus b1 u1. Okay, so then what happened? Okay, what happened then when I have k equals to 2? I'm going to write for all the data that I have. Okay, when k equals to 2, I have y3 equals to minus a1 y2 plus b1 u2. When k equals to 3 is going to be y4 minus a1 y3 plus b1 u3. Okay, so then what if I have, when I have k equals to 4? Because I have k equals to 4 data, isn't it? So what happened when k equals to 4? When k equals to 4, y that we have here is y5. Okay, y5 is equals to a1 y4 plus b1 u4. Okay, what is the problem in this particular example? So for this equation now, you look at this equation. When k equals to 4, we have this. Okay, this is what we have, this y5. Okay, y5 here is actually you don't have the data y5. So even though if you can use this equation, but you don't have the data for y5, so it is useless, isn't it? So you cannot do it. So what happens is that for this 4 data, we're going to ignore what happened when k equals to 4, simply because we don't have y5. So y5 is not there. So we cannot use this last equation. Okay, so I'm just going to focus with the first three equation. Okay, so what if I put these 3 equation in a matrix form? So if I put these 3 equation in a matrix form, this is what going to happen. Okay, so I put in a matrix of y2, y3, y4. Okay, it is a matrix equivalent to, I'm going to put the minus y1, u1, minus u2, y2, u2, minus y3, u3. Okay, so what happened is then I will multiply this with the 2 unknown parameter that I need to estimate, isn't it? Which is a1 and b1. Okay, so using these 3 equation that we have derived earlier, okay, we then later on write down in a matrix form. Okay, and then we come up with this matrix. All right, so let's call that matrix, the first one here, let's call that y. The second one, let's call that phi. Okay, and for the parameter, let's call it beta. Okay, let's call it beta for the parameters. All right, so using least squared, as I'm going to use, because I have the data, all these data I have. Okay, I have y1 until y4, so I'm going to use all this data, put this back in this matrix form. Okay, so I'm going to use all the data that you've seen in the slide here. I'm going to put it in the matrix form. All right, so I will start with the y matrix. I will start with y2, isn't it? Okay, because of the equation says start with y2. So y2 is 4, y3 is minus 12, y4 is minus 4. Okay, so this is equivalent to the phi. I'm going to put values in phi, whereby phi is actually a collections of data between the minus y and u. Okay, so I'm going to put the minus y1, y1 is 12, so if we put minus into it, it becomes minus 12. Okay, y2 is 4, if I put minus into it, I have minus 4. Then y3 is a minus y3. Y3 is 12 minus y3 is positive 12. Okay, so similarly for u, I'm going to put u1 here, 1. u2 is minus 1 and u3 is minus 1 as well. Okay, so that is my phi matrix. You can see that we do not need to use the y4 and u4 in our phi matrix. Okay, this is because we don't have y5. Okay, just now for the equation that we ignored earlier. Okay, then this is multiplied with my parameter a1 and b1. All right, so this is y, this is phi, and this is beta. Okay, so y is for least squared, we're gonna use y is equals to phi multiplied by beta. For this equation, we're going to use least squared algorithm to find the parameter of a1 and b1. Right, so how to do that? Based on least squared estimation, if you read in textbook, it is saying that for this equation, the least squared estimation for beta is equivalent to phi transpose multiplied by phi inverse it. Okay, so it is actually in the slide. Just scroll through the slide. Okay, so I put all this equation that I have written just now. It is actually in the slide. Okay, so you can refer back to my slide later on. Alright, so for the least squared estimation, we're going to use phi transpose phi inverse multiplied by phi transpose multiplied by y. Okay, so there are two parts that you need to do. The first one is you need to get your phi. This is the matrix for your phi just now. Okay, so you need to take this matrix for phi. Okay, right, and then you need to actually inverse it, all right, and then transpose it and multiply with phi transpose and then invert it. Okay, so how to transpose phi? So once you have that phi in that form, okay, what you need to do is transpose it. So phi, so phi transpose is just all the row become column and all the column become row, isn't it? Minus 12, minus 4, 12, and then you have 1, minus 1, minus 1, and then you need to multiply that with your phi. Let me just write it here again. Okay, so I need to multiply that with phi again. Phi is minus 12, minus 4, 12, 1 minus 1 minus 1. Okay, so when I have multiplied that, okay, it become the one that you've seen in the screen. You can try this on your own. You will get this value here, 304. Okay, minus 20, minus 20, and 3. Okay, so you can try and do the matrix multiplication later on and check if the value is correct or not. Then using this value of phi transpose phi, you need to then inverse it. Okay, so how to inverse phi transpose phi? Okay, so since you already have that value 304 minus 20, minus 20, and 3, inversing it going to be like this. Phi transpose phi inverse is going to be, it is 1 over 304 multiplied by 3 minus 20 multiplied by minus 20. Okay, and then for the matrix is going to be inside here is going to be the 304 and 3 will change in location, in position. So you're going to have 3 and 304 change in position, and then the minus 20 will become a negative sign of it. Okay, so negative 20 with negative 20 become positive 20. Okay, so that's how you do inverse matrix. I hope you still remember this. Okay, so once you have done that, you will see that by calculation it become 1 over 512, 3, 304, 20, and 20. Okay, so as soon as you got this, then you need to have the other part of the equation, which is phi transpose multiplied by y. So I already have the phi transpose just now, so then I need to multiply that with y. So what was the value of phi transpose just now? Minus 12 minus 4, 12. 1 minus 1 minus 1. Then I need to multiply that with my y. So what was the y just now? The matrix for y is 4 minus 12 minus 4. 4 minus 12 minus 4. So once you do this multiplication, okay, you're going to get a matrix minus 48 and 20. Okay, that is the matrix that you're going to get by doing this multiplication of phi transpose and y matrix. Okay, so once you already have that, then we can find out the least squared estimation of the data that we have just now. So based on least squared parameter estimation, is stated that beta is equals to phi transpose phi inverse, okay, multiplied by phi transpose y. Okay, so once you have that phi transpose phi inverse multiplied by phi transpose y, what you're going to get, that you're going to put all these all the matrices that you have calculated earlier. Okay, and then multiply with this matrix of phi transpose y. Okay, so when you do that, what's going to happen is that you're going to get a matrix of 2 by 1, which is 0 0.5 and 10, and this is actually your beta, okay, the estimated parameter of your system. So since beta is consisting of, just now if you remember, it is A1 and B1, so this is equivalent to 0 0.5 and 10. It means to say that your equation, your parameter that you estimated for A1 using this very limited data is equals to 0 0.5, and the parameter that you estimated B1 is equals to 10. Therefore, it means to say that your system is having a transfer function looking like this. This is your estimated transfer function, okay? When you apply input u to the system, your system will look like this. It's going to be 10z minus 1 over 1 plus 0 0.5 z minus 1. Then you get your output y. Okay, since you already estimate the parameters, okay, you already got the parameter which is A1 and B1. What you can do is you can put back this parameter into the original ARCS equation, and then you can do the predicted output of this. Okay, let's do that. Let's predict the output using the estimated parameter. So normally for estimated parameter, I will put hat on top of it, okay, and similarly for B1, I'll put a hat on top of it. Okay, so how do I do this? It based on the previous equation of yk. If you remember, yk is equals to, so of course, sorry, it's not yk, it's yk plus 1 is equals to minus a1 yk plus b1 uk. So we're going to use all the data that we already have for yk, okay, based on the slide earlier. If you remember, if you look at the slide just now, okay, that was the data. Okay, so let's use that data again and check if your predicted output is similar to your actual output. And from there, you can calculate the error that you have, if any error is appear within this predicted model. Okay, so when k equals to 1, my predicted y2 is equals to minus 0 0.5 y1. So from the table, y1 is 12, okay, plus B1 is 10, U1 is 1. So from there you can get your output is minus 0.5 multiplied by 12 is minus 6. Minus 6 plus 10 is equals to 4. So it seems that your predicted output is equals to your actual output, because if you look at the table, the actual output is 4. All right. Okay, the actual output when y is equals to 2, when k equals to 2, y is equals to 4, which is similar to your predicted output. Therefore, you can write the predicted error. For error y, it's equivalent to, for error at time k equals, hang on, let me write this. Okay, for error at time k, it is equals to the actual output y at time k minus the predicted output y at time k. So in this case, it's 4 minus 4 equals to 0. So you do not have error for this prediction, which is very, very good, isn't it? So for k not equals to 2, you're going to get a predicted y3 is equals to 0.5 multiplied by your y2. Y2 in this case is 4 plus 10 multiplied by minus 1. So again, for this one, you're going to get the result is going to be 0.5 multiplied by 4. It's 2 with a minus 2. Minus 2 minus 10 is going to be minus 12. And again, the error is exactly 0 for this, isn't it? Okay, error for time k is equals to minus 12 minus 12, which is 0. Okay, and lastly, you're going to predict with k equals to 3. You're going to have y predicted 4 is equals to negative 0.5 multiplied by your y3. Your y3 is minus 12. Okay, plus 10 multiplied by your u3. Your u3 is minus 1. Okay, so you put that in the equation, and then you're going to calculate minus 0.5 multiplied by minus 12 is going to be giving you 6. Okay, 6 plus minus 10 is going to give you minus 4. So minus 4 is exactly the actual output, is equivalent to the actual output to the system. So your prediction error for this data number 3 is equals to minus 4 minus 4, which is also 0. So for this least squared estimation, it's proven that A1 and B1 is actually the predicted output, and is with this predicted output, it gives a very small error, which is 0 error to this particular data. Okay. Okay, so I put this in the slide. You can then use it. All right. So for the next class, all right, what I want you to do, I want you to go through this slide and then go through this again, one past year questions back in 2007, which is the least squared estimation using another another set of data with 4 data. So I already have the solution here. Actually, it's a very similar activities. Using ARCS model, all right, I'm going to estimate the parameters. So it's actually using the same activity. What I'm going to do is I will write down the ARCS equation in the form of y equals to phi transpose b beta, and then the parameter that we need to estimate is in beta form. Okay, so put all the data into this matrix form. Okay, and again compute for your phi transpose phi transpose phi, and then inverse it, and then multiply with phi transpose y. Then you're going to get your parameter estimation as 0.5, 55, and 2.4. Okay, so hang on. Okay, so if you look at this estimation, 0.55 with B1 and A1, and for B1 is 2.5. When I use this, when I use this in the slide, when I put back in the equation and then try to find the error of my estimation, my prediction error, again similar as before, okay, I'll get for y predicted 2 is equals to 4.7, y predicted 3 is equals to negative 0.25, for y predicted 3 it's equal, y predicted 4 is equals to negative 2.5. So using this value, I then put a column, a row in my table just now with a predicted value and predicted error. So I'll get the error of 0.3, 0.25, and 0.5. So from there, I calculate the mean squared error. So what is mean squared error? It is just the error 1 square plus error 2 square plus error 3 square, and then find the mean of it. So it's giving me 0.134. Okay, so that's all for least squared estimation. So I will come back again for the next class. I will talk about generalized least squared. Thank you so much for your attention.